Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the communication systems IES or ESE Prelims examinations of previous year questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever you upload a new video, the direct notifications comes from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 141 question. See the question here. The Nyquist sampling rate for the signal g of t is equal to 10 cos 50 pi t into cos square 150 pi t, where t is in seconds. So for this question we have to find, there is a signal g of t. For this signal we have to find what is the Nyquist frequency. So Nyquist frequency is called as the minimum sampling frequency. So here out of the four options, option D, 350 samples per second. 350 samples per second is the Nyquist frequency, and option D is the correct solution of this question. So let's solve this numerical. So basically this is a signal g of t. They are giving the question which is 10 cos 50 pi t into cos square 150 pi t. So for this signal we have to find what is the Nyquist frequency we need to figure out. So if you see carefully, this is cos square some theta. So I want to convert in terms of cos theta. So what I am going to do here, cos 2 theta is equal to 2 cos square theta. So here cos square theta is equal to cos 2 theta plus 1 by 2. So here theta is equal to 150 pi t. So after simplifying this, I am going to get in this fashion. So here this 2 is going to come outside, so therefore 10 by 2 is called as a 5. So 10 by 2 is 5. So therefore 50 cos 50 pi t. So I am going to make it here into division, just cos 300 pi t plus 5 cos 50 pi t. So this is in the format of cos a into cos b. So where cos a into cos b is equal to half of cos a plus b plus cos a minus b. So I am going to make in this fashion, which is 5 by 2 cos of 350 pi t plus cos of 250 pi t. So plus 5 cos 50 pi t. So I want to know what is the frequency of each and individual signal I want to figure out. So let me take this is the message signal 1 frequency, which is 350 pi by 2 pi, and also the frequency of the second signal, which is FM2 is equal to 250 pi by 2 pi, and also the frequency of the third signal FM3 is equal to 50 pi by 2 pi. So therefore now after simplifying this, I am going to get 175 Hertz, FM2 is equal to 125 Hertz, and FM3 is equal to 25 Hertz. See, as the sampling frequency, always has to be greater than twice the maximum message signal frequency. So this Nyquist frequency is called as the minimum sampling frequency. So minimum sampling frequency is called as the Nyquist frequency, which is equal to twice the message signal maximum frequencies. So out of all the message signals, we have to take only the maximum message signal frequency. So same thing I have used here. So Nyquist frequency is equal to twice the maximum value of all the individual message signal frequencies. So out of all the message signal frequencies, you have to take only that maximum value. So therefore out of FM1, FM2 and FM3, the maximum value is 175. So therefore you have to keep here. So 2 into 175 is nothing but 350. So therefore the Nyquist frequency is 350 Hertz, or we can say 350 samples per second. So therefore each and every second it is going to sample, at 350 samples are going to sample in 1 second. So this is the correct solution of this question. So now we are going to solve the 142nd question. See the question here. What is the condition for which slope overload error occurs in a delta modulation to the input m of t is equal to at for t greater than 0, where the step size is d and the sampling rate is fs. So based on this message signal and this step size d and the sampling rate fs, so we have to find what is the condition for the slope overload which is going to occur in the delta modulation. We need to figure out. So out of the four options, option A is the correct solution of this question, which is d by ta less than a is the correct solution of this question. So let's solve this numerical. So in this question they are given that the message signal is equal to at for t greater than 0. So for t greater than 0, this is the waveform of the message signal. So in this question they are asking what is the slope overload. The slope overload occurs in delta modulation at what is the condition they are asking. So basically see here the graph here, m of t is said to be a message signal and m cap of t is called as a staircase waveform. See, for t greater than 0, so for t greater than 0 we are going to analyze these waveforms. So here m of t is equal to a into t, means it is a ramp waveform. So we are going to get a ramp waveform. So always the staircase waveform, it is going to generate in the delta modulation. So therefore this is a waveform we are going to get in the delta modulation of the staircase waveform, which is called as the m cap of t. So therefore here this small width is called as a TS and the small height is called as a step size. So in some textbooks they will use delta is equal to, we can write even delta we can replace with d, it is called as a step size. So this small length is called as a TS and this is called as the delta. So here what is the condition for this slope overload in the delta modulation? See, whenever the positive peak value, so maximum positive value of the rate of change of message signal should be greater than the maximum positive value of the rate of change of the staircase waveform. At this condition only we are going to get the slope overload error which is going to occur in the delta modulation. So therefore I want to do the derivative of this message signal m of t with respect to time. So therefore d by dt of m of t will give a value and it has to be only a positive value. So therefore here this modulus is going to implies that we have to take the maximum positive value itself. So therefore we are going to get the a value. It has to be greater than. Now I want to know what is the maximum positive value of the rate of change of the staircase waveform. So therefore I want to know what is the slope of this one. Slope is nothing but delta y by delta x, where delta y is the delta, means here the height is called as the delta and the width is called as the ts. So therefore this is the slope of this staircase waveform. So therefore delta by ts. So therefore I can write in another fashion also. If a greater than delta by ts, I can write in another fashion which is delta by ts less than a. So therefore delta is nothing but we are going to replace delta with, in a few books they are going to replace delta by d. It is called as the step size. How much is the height of the staircase waveform? So therefore d by ts less than a. So therefore at this condition we are going to get the slope overload error which is going to occur in the delta modulation. So therefore this is the correct solution of this question. So now we are going to solve the 143rd question. So the question here, which one of the following signals can be applied to a delta modulator whose step size is 0.1 volt and the sampling frequency is 20 by kilohertz so that no slope overload occurs? So basically in this question they are given the delta value, means the step size is 0.1 volt and also the sampling frequency, means the sampling frequency they are also given which is equal to 20 by kilohertz. So based on this we have to know what is the condition for the no slope overload. So therefore no slope overload is going to occur in the delta modulator. So for which message signal? So out of the four options, option D is the correct solution of this question. For the option D message signal, we are not going to get any slope overload is going to occur for this delta modulator. So let's solve this numerical. So in this question they are given that the step size is equal to 0.1 volt and also here the sampling frequency is equal to 20 by kilohertz. So here for this delta modulator, when we give you what input we have to give, so therefore there will be no slope overload error is going to occur. So what is that message signal we need to figure out? So these are the four options, A, B, C, and if you say carefully here, everything is in terms of sine waveform with some peak value. So therefore here I am going to take a general expression of the message signal m of t is equal to Vm sine 2 pi fmt. So I want to do what is the derivative of this message signal, d by dt of m of t. If you do this one, sine differentiation is cos 2 pi fmt, and if you do the differentiation inside we are going to get 2 pi fm into Vm. So this is the thing we are going to get, but we need only the maximum positive value, of this d by dt of m of t. So therefore this model is going to indicates we have to take only the maximum positive value of the d by dt of m of t. So the maximum positive value is only which is Vm into 2 pi fm. So therefore here the slope overload is not going to occur in the delta modulator whenever the maximum positive value of the d by dt of m of t is lesser than or equal to maximum positive value of the d by dt of the staircase waveform. At this condition there will be no slope overload error is going to occur in the delta modulator. So therefore here, if you see carefully here, we know the value of this one. So therefore substitute this one, Vm 2 pi Fm. So and also less than or equal to, I have already told you the staircase waveform. The staircase waveform is going to be like this shape. So therefore this is called as a delta and this is called as a Ts. So I want to know what is the slope. Slope is this by this value. So therefore delta by Ts. So therefore 1 by Ts is nothing but sampling frequency. So 1 by Ts is called as a sampling frequency because sampling frequency is equal to 1 by Ts. So therefore 1 by Ts means we have to keep here Fs. So therefore at this condition, so whichever the message signal which satisfies this condition, then we can say that message signal, if you give input to this delta modulator, we are not going to get any slope overload error is going to occur. So therefore here delta value they are given, which is 0.1 volt, and also Fs is equal to 20 pi kilohertz, and if you do the multiplication of this delta and Fs, we are going to get 2000 pi. So therefore here finally now I am going to make this delta Fs is equal to 2000 pi. So whichever the signal which is going to satisfy this condition, I am going to say, which is Vm 2 pi Fm has to be less than or equal to 2000 pi. So whichever the signal satisfying this condition, we can say there is no slope overload error. So therefore see carefully, there are 4 options, A, B, C, D. So I am going to solve this condition for each and every message signal, and I am going to check this condition. So whichever the message signal satisfy this condition, then we can say that message signal, if you give input to this delta modulator, we are not going to get any slope overload. So therefore if you take the option A, which is 2 into sine 1200 pi t. So therefore the peak value Vm is equal to 2, and here 2 pi Fm is equal to 1200 pi. And if you do the multiplication of this one, Vm 2 pi Fm should be less than or equal to 2000 pi in order to be no slope overload. But if you see, we see whether this is satisfied or not. So therefore Vm into 2 pi Fm, we are going to get 2400 pi less than or equal to 200 pi. No, this is always 2400 is always greater than the 2000 pi. So therefore this condition is failed. So therefore we can say for this message signal, if you give the option A, which is a message signal, yes, we are going to get the slope overload error is going to occur. And take the option B, which is 1 sine 2600 pi t. So again the peak value Vm is equal to 1 volt and 2 pi Fm is equal to 2600 pi. So for no slope overload condition, this is we need to figure out. So if you do the multiplication of these two things, we are going to get 2600 pi less than or equal to 2000 pi. No, actually 2600 pi is always greater than 200 pi. So therefore this condition is also failed. So therefore if you give this message signal as an input, then we are going to get the slope overload is going to occur. And if you take the option C, 3 sine 1000 pi t. So the maximum peak value is 3 volt and 2 pi Fm is 1000 pi. And if you the condition for the no slope overload is this is the thing. So if you substitute these two values, we are going to get 3000 pi. But 3000 pi is always greater than 2000 pi. So we can conclude that this condition is also failed. So therefore we can conclude that if you give input as this signal, we are going to get slope overload is going to occur. And the remaining option is option D. If you check here, 4 sine 400 pi t. The Vm is equal to 4 volt and 2 pi Fm is 400 pi. So this is the condition for the no slope overload. So let's see whether this is satisfied or not. And if you do the multiplication, we are going to get 600 pi less than or equal to 2000 pi. Yes, the 600 pi is less than or equal to, it is less than the 2000 pi. So therefore this condition is satisfied. So out of 4 options, only option D message signal is going to satisfy this condition. So we can say if you give this 4 sine 400 pi t as an input to a delta modulator, then there is a no slope overload error is going to occur. So therefore option D is the correct solution of this question. So now we are going to solve the 144th question. See the question here. Slope overload occurs in delta modulation when the, so slope overload is going to occur in the delta modulation when, so at what options, at what conditions we are going to get the slope overload in the delta modulation, we need to figure out. So what are the 4 options? Option C, when the step size is too small. So when the step size is too small for the staircase waveform, yes, then we are going to get the slope overload is going to occur in this delta modulator. So let's discuss something more about this one. So in this question they are asking at what reason or at what condition we are going to get the slope overload is going to occur in this delta modulator. So if you see carefully here, suppose this is called as a message signal. This is the message signal which is input to a delta modulator, and this is the output of the delta modulator signal, or we can also call it as a staircase waveform, which is m cap of t. So therefore here I want to know what is the slope of this m cap of t or staircase waveform, which is delta by ts. So whenever the rate of change, or we can say whenever the rate of change of the message signal is greater than the rate of change of the m cap of t or staircase waveform, then we are going to get the slope overload condition, or the rate of change of this message signal when it is greater than the rate of change of this staircase waveform. Yes, at that condition we are going to get the slope overload error is going to occur in this delta modulator. So therefore the slope overload is going to occur in the delta modulator whenever the rate of change of the message signal or the slope of the message signal is greater than the rate of change of the output signal, or we can say the rate of change of the staircase waveform. So therefore we can say in another terms also, this is a positive peak value of the rate of change of message signal is greater than the positive peak value of the rate of change of the staircase waveform or the output of the delta modulator. So at this condition we are going to get the slope overload error is going to occur in this delta modulator. So here suppose I want to know what is the rate of change of this staircase waveform. So I want to find what is the positive slope. So therefore delta by ts is called as a positive slope for this rate of change of the slope of the staircase waveform. So therefore d by dt of m of t should be greater than delta by ts. So this value will be higher when this value will be lesser. So therefore here see, if delta is decreasing, so when a step size is decreasing, so what is going to happen, this term will become very low value. So when this value is going to become low value, automatically this value will be higher. So therefore at that condition, so therefore whenever this value is very lower, then automatically this value will be higher. So therefore this condition is going to get satisfied. So when delta is decreasing, so when delta is going to decrease, yes, this condition is satisfied. So whenever this condition is satisfied, we can conclude that yes, slope overload is going to occur in this delta modulator. So therefore delta is called as the step size and ts is called as a sampling time interval, which is the reciprocal of the sampling frequency, which is 1 by fs. So therefore there is, see, this d by dt of m of t is called as the rate of change of message signal, or we can say positive peak value of the maximum positive peak value of the rate of change of message signal, we can say in that fashion also. Or d by dt of m cap of t with mod, we say it as a slope at output of delta modulator, or we can also say which is the rate of change of the staircase waveform, positive peak value only we need to figure out. So therefore with this condition we can say whenever the slope of the message signal is higher than the slope of the staircase waveform or the output of the modulator, yes, at that condition only we are going to get the slope overload is going to occur. So this is going to occur whenever this value should be very lower. This value will be lower when this delta value decreases. When delta value decreases, automatically this condition is satisfied, then the slope overload is going to occur in this delta modulator. So therefore this is a correct solution of this question. Whenever the step size decreases, yes, slope overload is going to occur in this delta modulator. So this is a correct solution of this question. So now we are going to solve the 140th question. See the question here. Which one of the following PCM schemes, pulse code modulation schemes, is depicted in the below figure? So out of the following below PCM schemes, so this circuit is going to represent which one? So what are the four options? So out of four options, option D is the correct solution of this question. So this circuit is the circuit which is shown in the figure. It is going to resemble with the delta modulation scheme. So let's discuss something more about this one. So in the question they are given this circuit. So here this circuit is going to resemble which type of circuit in the PCM schemes we need to figure out. So if you see carefully, here there is a message signal. I am going to assume the message signal is S of t, and there is also a comparator. So comparator, based on these inputs A and B, it is going to compare the signals. See, whenever the A is greater than B, so we are going to get a negative step signal we are going to get. So whenever the A is less than B, then we are going to get a positive step. So these two inputs are given for a staircase generator. So with the help of these two inputs at these two conditions, yes, we are going to get a staircase waveform. Here we are going to get. So this is the function of this circuit. So here, out of PCM schemes, which circuit is going to resemble this type of circuit we need to figure out. So if you see carefully here, for the delta modulation transmitter, so this is the circuit of the delta modulation transmitter. So therefore here there is a message signal M of t, and also here we are going to use the low pass filter, because generally the message signal will have large range of frequencies, but we can't transmit each and every frequency. But so with the help of low pass filter, we are going to cut down the frequencies to a finite value, and then we can easily transmit them. So because of that reason only we are going to use this low pass filter, and we are going to give input to this comparator, or we can say op amp. So basically this op amp has no feedback, no positive feedback or negative feedback. So therefore we can say this is going to act like a, so this is going to act like a comparator. So therefore here there is a quantizer. So with the help of quantizer, whatever the output pulse we are going to get, we are going to quantize to a particular levels, to a finite levels. So therefore with the help of standard levels, we are going to represent any number of infinite number of peak levels. We are going to quantize to a standard peak levels. So therefore again we are going to modulate with respect to the pulse train, and then we are going to encode this signal into a digital value. So therefore this is all about this one, and this the signal at this junction we are going to integrate, and then we are going to get the staircase waveform. See, basically same thing, this circuit and this circuit are going to resemble same thing, because there is a comparator, and because of integrator we are going to get the staircase waveform. Same thing here also, because of staircase generator we are going to get the staircase waveform, and also there is a comparator, and these are the conditions. So these two circuits are going to resemble or function in the same manner. So we can say this circuit is resembles to a delta modulation transmitter. So therefore this is the correct solution of this question. So now we are going to solve the 146th question. See the question here. Assertion. This is a assertion reason type question. So assertion is slope overload is a problem in the differential pulse code modulation, and the reason is differential pulse code modulation makes use of adjacent sample correlations. So we need to find, so whether assertion is correct or reason is correct or false, we need to check. So what are the four options? Option D, assertion is false and the reason is correct. It is the correct solution of this question. So let's solve this question. So in the delta modulation, yes, the slope overload problem is going to discuss. So in the delta modulation, the slope overload is going to occur. So at what condition? We already discussed the rate of change of the message signal when it is greater than the rate of change of the staircase waveform, or we can say output of the signal, output of this delta modulation. So at this condition, yes, we are going to occur, the slope overload is going to occur. So now differential pulse code modulation. So the slope overload concept is not related with the differential pulse code modulation. So therefore assertion is wrong. In the assertion they have given that the slope overload is a problem in the differential pulse code modulation. No, because the slope overload concept is going to relate only with the delta modulation. It is not going to have any relation with this delta pulse code modulation. So therefore assertion is wrong. Now we will see why the reason is correct here. See here, in the reason they have told that here the differential pulse code modulation makes use of adjacent sample correlations. Means, see, differential pulse code modulation transmitter. This is the differential pulse code modulation transmitter. So therefore this is a message signal. So with the help of sampler it is going to give a digital signals, and then here there is a circuit in this fashion. So because of this circuit, the new each word is equal to current sample minus previous sample value. So therefore here there is a plus and there is a minus. So therefore whatever the new word we are going to get, our new output is equal to current sample value minus previous sample value. So because of this difference we are going to get the new word. So therefore each new word is equal to current sample value minus previous sample value. So therefore in order to get a new sample value, it is going to use the two things, which are the current sample value and also the previous sample value. So because of this one, because it is going to use the difference of the current sample value and previous sample value. So we can conclude that here there is a feedback and also there is a correlations between the input signals. So we can conclude that yes, DPCM makes use of adjacent sample correlations. So in order to get a new value, it is going to use even the previous sample value. So because of this reason only, this DPCM, yes, it is going to use this adjacent sample correlations. So therefore we can conclude that here the slope overload problem is going to occur only in the delta modulation. It is nowhere related with the differential pulse code modulation. So and also in differential pulse code modulation, yes, the adjacent sample correlations is going to occur because in order to get a new word, it is going to use the current sample value and also previous sample value. So because of this reason only, the reason is correct and the assertion is wrong. So now we are going to solve the 147th question. See the question here. The performance of the differential pulse code modulation coder improves as the. So here the performance of the differential pulse code modulation is going to improve at what condition? So out of the four options, option D is the correct solution of this question. Means whenever the sample to sample correlation of the input increases. So whenever the sample to sample correlation of the input increases, so we can conclude that here the performance of the differential pulse code modulation is going to increase. So let's discuss why this is going to happen. So this is the differential pulse code modulation transmitter. So therefore this is a transmitter of the differential pulse code modulation. So this is the message signal and this is the sampler. So with the help of this one, we are going to get the samples of the signal. So we are going to get the samples of the signal here. And here, because of quantizer, so if there are so many infinite number of positive peak values, so we are going to confine to a minimum number of quantization levels. So with the help of quantization levels, we are going to give a finite number of levels here. So then we are going to use the encoder and then we are going to convert in terms of the digital signals, or we can say number of bits. So this NB is going to represent the number of bits which are present in the output of this encoder. So here I already told you, in the differential pulse code modulation, always the each new word we are going to get, which is the current sample value minus the previous sample value. So if the sampler is going to perform more number of samples, means the frequency Fs is very higher, then the number of samples we are going to produce is a very higher. And also the difference means whenever these samples are very higher, these operations are also increased. So whenever these operations are increased, so therefore here encoding is also going to be increased, because we are going to get the quantizer as so many number of nearly equal to the standard levels, or we are going to get, because whenever the sample is going to increase, we are going to get the samples which are nearly equal to the standard levels. Then the encoder performance is also going to increase. So whenever the encoder performance is increases, the number of bits at the output are also going to decrease. So we can say as the sampling is increases, the encoding performance increases and the number of bits at the output we can decrease. So therefore the performance of the differential pulse code modulation of the transmitter, it is going to increase. So basically the DPCM, the differential pulse code modulation, the performance is going to increase whenever the sample to sample correlation is going to increase at the sampler. So this is all about this one. So now we are going to solve the 148th question. See the question here. One disadvantages of the adaptive delta modulation over the linear delta modulation is that is. So we have to find what is the disadvantages of the adaptive delta modulation when compared to the linear delta modulation. So what is that? So out of the four options, option C, it requires a large number of comparators in the encoder. So basically in this adaptive delta modulation, we are going to use the more number of comparators in the encoder. Then we will see why like this. So option C is the correct solution of this question. So now we'll discuss some of the important points of the adaptive delta modulation and the linear delta modulation. So if you see carefully here, in the linear delta modulation, there is a granular noise and also slope overload problem. Yes, whenever the slope of the message signal is greater than the slope of the staircase waveform, then we are going to get the slope overload problem. And also there is a feedback present in the circuit, and because of the quantizer is present in the circuit, yes, we are going to get the condensation noise is also going to present. Basically this condensation noise is going to act like a white noise because it is going to alter only the signal of the amplitude. So therefore these are the three things which are going to present in this linear delta modulation. So now when compared to adaptive delta modulation, because of this advantage, because of these disadvantages, so we are going to go for the adaptive delta modulation. So therefore here we are going to remove these two noises. So therefore granular noise is going to absent here, and also slope overload problem is also absent in this adaptive delta modulation. But here also there is a feedback and here also there is a quantizer. So because of that reason the quantization noise is also present in both the linear delta modulation and also the adaptive delta modulation. And also here the comparators in the encoder are very higher in the adaptive delta modulation, but the comparators are very low in the encoder. So this is considered as one of the disadvantages of the adaptive delta modulation when compared to the linear delta modulation. And also here for the adaptive delta modulation, where the step size is a variable, so based on the input the step size can be a variable value. But for a linear delta modulation, no matter whatever the message signal, always the delta value is a fixed value. So therefore here delta is fixed for each and every message signal, but the delta value is variable for the adaptive delta modulation. For message signals, if they are going to vary, then delta is also going to variable. So we can consider there is a highly dynamic range. Dynamic range is very wider because the delta can be a variable, whereas dynamic range is very less because for each and every message signal the delta is a fixed value. So therefore we can conclude that the dynamic range of the delta modulation is very less when compared to the dynamic range of the adaptive delta modulation. And also I've already told you there is a feedback between the output and input in both the circuits. So finally I am going to conclude that, so here the comparators in the encoder is very high in the adaptive delta modulation when compared to the linear delta modulation, and this is considered one of the main disadvantages of the adaptive delta modulation over the linear delta modulation. So now we are going to solve the 149 question. See the question here. Which one of the following multiplexing techniques involves signals composed of light beams? So here, in which multiplexing technique we are going to use signals which are using the light beams? So the four options. Option D, in WDM. In this WDM technique, we are going to use the signals of light beams. So option D is the correct solution of this question. So let's discuss something more about this one. So now we'll discuss what is CDM. CDM is code division multiplexing, whereas FDM is frequency division multiplexing, and also TDM means time division multiplexing, whereas WDM means wavelength division multiplexing. So basically in the wavelength division multiplexing, we are going to use the fiber optics for communication. So whenever we are using fiber optics for communication, one thing is very much clear. So as by default, if you are using fiber optics means inside we are going to use the light beams for the communication. So therefore we can conclude that the light beams for the communication are going to be used default in the fiber optics. So therefore fiber optics, so this is called as the wavelength division multiplexing. So when in this technique we are going to use the fiber optics for communication means as default fiber optics indicates inside this we are going to transmit the light beams for the communication. So therefore we can conclude that in the wavelength division multiplexing we are going to use the fiber optics as a for communication, in that we are going to use the light beams as a purpose of communication. So now we are going to solve the last question of this lecture. See the question here. To overcome this slope overload problem, which type of integrator is used in the delta modulation? So basically in delta modulation there is a problem of slope overload. So if you want to remove that, what type of integrated circuit we must use in the delta modulation? This question they are asking. So what are the four options? Option B, variable slope integrator. So if you use the variable slope integrator, what happens? Basically it is going to remove the slope over slope problem in the delta modulator. So let's discuss something more about this one. So basically in the delta modulation always there is a slope overload problem. See, the slope overload problem is going to occur when the positive rate of change of the message signal is greater than the positive rate of change of the staircase waveform. When this is the case, then we are going to get the slope overload problem is going to occur. So the slope overload problem is not going to occur. The condition is when it has to be less than or equal to. So therefore when this rate of change of message signal, if it is less than or equal to rate of change of the staircase waveform, then there will be a no slope over problem is going to occur in this delta modulation. So what do we have to do in order to remove this slope overlap problem? So what we are going to do is we are going to make this as a equal. So whenever we are going to make this as a equal, then the slope overlap problem is not going to present in this delta modulation. So how we are going to make this slope of this message signal is equal to slope of this staircase? Because always we have already told you in delta modulation, always the value of the delta is fixed for each and every message signal, but we want to vary this delta. So because of this delta variation, this slope is also get changed. So whenever the slope of the staircase is going to change, we are going to try to make it the slope of this staircase is equal to the slope of the message signal. How means we have to vary this delta. So now how we need to vary this delta? Because if you see carefully, suppose let me assume this is a message signal. So therefore if you take at each and every instant, the slope of the message signal is varying. But if we make delta as a constant, then at certain times, yes, the slope of the message signal should be greater than the slope of the staircase, then the slope overlap problem might occur. So we have to change this delta at each and every time of the message signal, because at each and every time the message signal slope is also changing. So we have to change this value of the delta in such a way, so therefore we can make the slope of this m of t is equal to the slope of this staircase waveform. So we have to vary this as a, so delta should not be a fixed value, it has to be a variable factor. So how we are going to use, because this is a delta modulation transmitter. So if you see carefully here, this is a message signal and this is a low pass filter. I have already told you what is the true meaning of the low pass filter. In order to cut down these infinity frequencies to a finite frequencies, because we can't transmit infinity frequencies in a channel. So there is a comparator. So this comparator is going to compare the m of t and the m cap of t. So now what we have to do is, in place of a normal integrator, we have to keep a variable slope integrator. So we have to remove this integrator and we have to keep a variable slope integrator. So because of this variable slope integrator, now we are going to make this slope of m cap of t, or the slope of the staircase message signal, we are going to try to make it equal to the slope of the message signal. So therefore now at each and every instant we are going to make, then what is going to happen is, then the slope overlap problem is going to absent in this circuit. So we have to replace this message, this normal integrator with a variable slope integrator. Then we are at each and every instant we are trying to make the slope of the message signal is equal to slope of the staircase waveform. Then we are going to remove the slope overlap problem in this delta modulation. So basically in adaptive delta modulation also we are going to use this variable slope integrator, because that is the reason in the adaptive delta modulation there is a no way of the slope overlap problem. But so finally replace this integrator with respect to the variable slope integrator, then there will be a no slope overlap problem in this delta modulation, because we are going to make the slope of the message signal is equal to slope of the staircase waveform at each and every instant of time. So by this lecture we have successfully completed the 150 questions of the ESE or IES examinations regarding the communication systems previous year questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever you upload a new video the direct notifications comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.